In this video, we'll take a look at one proof technique that is useful when some others are not. This method is called the proof by contradiction. And the idea is that we kind of assume the opposite of what we know to be true, and then we show that that leads to a contradiction. So we know that a proposition, given a Boolean proposition, something that's either true or false, statement P, and its negation, the negation of P, one of these has to be true, while the other one has to be false. So I'll give you a basic example of this. Let's suppose P is the statement, it rained today. Well, the negation of that would be, it did not rain today. And as you can see, one of these is true and one of these is false, because either it rained or it didn't. There's nothing in between. If rain droplets hit the ground, it rained. If no rain droplets hit the ground, it did not rain. So we can prove that it rained today. And the way we could do this is we could go outside and say, hey, look, there's water on the ground and there's water coming from the sky. It rained today. Another way to prove this statement, it rained today, that is true, is by assuming the opposite. In other words, assuming the negation. Assume it did not rain today. Okay, well, let me walk outside and, hey, there are droplets all over the ground, assuming it's not water, assuming it's kind of everywhere. And I could say, well, that's a contradiction, because how could there be water everywhere if it didn't rain? And maybe there are some fringe examples of where maybe it didn't rain, but something else happened. But hopefully that makes sense, that we can assume the negation of what we believe to be true, and then we can show that that leads to some sort of contradiction, right? So an example of a common day contradiction would be to say that I say that the Arizona Cardinals are going to win the next game, and then I say that the Arizona Cardinals are not going to win the next game, right? Well, that's a contradiction, because both of those things cannot happen. And that is the definition of a contradiction, where two things cannot simultaneously be true. So one way to prove a statement is via direct proof, right? So we could show directly that, hey, look, there's water droplets on the ground, it rained. Another way is to show that the negation of the statement is false, and therefore the statement itself must be true. So here's a kind of a classical example of this. The square root of 2 is an irrational number. This is kind of a classic contradiction proof. And this proof is difficult for one primary reason, and that is, what is an irrational number? Well, we could kind of define that in terms of what we've seen before, like pi is an irrational number because it has two characteristics. It is non-repeating and non-terminating. And that's maybe what we learned to be an irrational number, but an irrational number is a number that is not rational. So a rational number, if you recall, it's the set of all rational numbers is defined by this kind of fancy looking Q. It stands for quotient. And it's the set of all numbers, A divided by B, or whatever you want the letters to be, such that A and B are both integers. So they're elements of the set of integers. We could write that out in words if we want. And B is not equal to 0. We can't have 0 in the denominator. So what does it mean to not be rational? Well, it means that it is not a ratio of two integers where the denominator is non-zero. And that's really difficult to prove what it is then, right? We just know what an irrational number is not. So it's really hard to work with this irrational portion. But let's look at the negation of this statement. If this right here is the statement P, the square root of 2 is an irrational number, then the negation of that is a much nicer statement. It would be the statement, the square root of 2 is a rational number. Okay, so it's either rational or it's not. Those are polar opposites, right? If it's an irrational number, we just know it's not expressible as a ratio of two integers. And what that often leads to is non-repeating, non-terminating numbers. You can't really represent pi as a fraction of two numbers in its exact form. In fact, pi goes on forever, and we have not found a repetition in that number yet. Okay, so let's actually work with this. Let's assume the square root of 2 is a rational number. Okay, we're going to show that this cannot possibly be. Okay, this is the beginning of our proof. All right, well, here is where we make a claim, and we say, well, first of all, a rational number is, as we know, a ratio of two integers, and there are infinitely many ways to express an integer as a rational number, right? So for example, 6 divided by 2 is a rational number, but in its simplest form, we know that that is 3/1, right? Every rational number can be reduced until it cannot be reduced any further. 7 divided by 5, well, that's also rational, but that is irreducible, so that's just left as 7/5. 9/12 we could reduce, and that could either be 18/24, so if you reduce it down, well, both top and bottom are divisible by 3, so we could reduce that and call this 3/4. Okay, so let's make that assumption that not only a square root of 2 is a rational number, but let's also assume that we have it expressed in reduced form. Let's say it is in reduced form. It is in reduced or simplified form. Now, that's not a strong assumption, right? Because every number is either reducible or it's not. So 7/5 can't be reduced any further. So there it is. Okay, so that means also that square root of 2, since it's a rational number, is equal to some integer divided by some other integer. Where, since it's a rational number, a and b are both integers, and b is not equal to 0. Okay. Once again, we know that this is going to be a false statement, but we're going to have to run into a place where that leads to a contradiction. Okay, so what can we do with this? Well, now we have an equal sign in there, right? If it's an irrational number, I can't say square root of 2 equals anything because I don't know the structure of an irrational number. I just know that it's not a ratio of two integers. Okay, so we could further manipulate this, and we could say, all right, well, let me square both sides. 2 equals, if I square both sides, a over b squared. Remember, if you square a fraction, that's the fraction times itself. When you multiply two fractions, you multiply their numerators. So essentially, you get 2 squared in the numerator, and you get 3 squared in the denominator. Yeah, it's the same thing as saying 2 squared over 3 squared. If you square a over b, that's going to be a squared over b squared. Okay, now this assumption of it is in reduced or simplified form, here's where we have to get kind of creative. If it's in reduced form, then that means that a and b aren't both even. Okay, let's think about that for a moment. If it's in reduced form, then a and b can't both be even. So 6 and 2 is not in reduced form, right? Because if it's an even number, then we know that we could factor out a 2. Now we could factor out a 2 here, make this 2 times 3, and here we can make this 2 times 1, and the 2's cancel out, and we get 3/1. So we'll also say over here, sometimes we have to backtrack a little bit and say, well, this means that a and b are not both even. Well, that means that necessarily, if a and b aren't both even, then either, I shouldn't even say either, we should say one or both of a and b are both odd, or one is even, the other odd. Okay, so sometimes we need to kind of unpack things. We don't necessarily know where we're going with things, but we want to walk into some sort of contradiction. Now, let's multiply both sides by b squared. Again, sometimes we just don't know where things are going, but let's see where this takes us. So if I multiply by both sides by b squared, the statement 2b squared equals a squared is a true statement that follows from the line above. Well, let's study this for a moment. And we see that we have the left side is 2 times an integer. Okay, it's a square of an integer, but it's still 2 times an integer. Because remember, an integer times an integer is itself an integer by the closure property of multiplication and addition of the integer. So in other words, we assume that when you multiply 2 integers together, you get another integer. When you add 2 integers together, you get another integer. That means that what I have here on the left side is, by definition, that is an even number. Well, the only way 2 things can be equal to each other is for them to be the same number, and that must mean that a squared itself, a squared must be even also. So I'm going to write this out. 2 times b squared is an even number, or is an even integer. Therefore, by equality, a squared is also even. Again, because the only way 2 things can be equal is if they're the same number. So if the left-hand side has an even number, that necessarily means that the right-hand side has to be an even number. Well, if a squared is even, a squared is equal to 2 times some integer. I'm going to have to introduce a new symbol. I'll say 2 times k, where k is an element of the integers. So a squared itself is an even number, which means a squared is equal to 2 times some integer. But let's take that one step further. The only way that you square a number and get an even number, the only number that I can multiply by itself and get another even number is an even number times another even number. So this also implies that a itself is even. Okay, so I'm going to back up here. Let me take off that squared. Okay, not only is a squared even, but a has to be even, since only the product of 2 evens is even. Okay, so you can't take a is the same number, right? It's a squared, a times a. So either a is even and therefore a is even, or a is odd and a is odd. And when we know that we've proven this before, that an odd times an odd is an odd number. Okay, that's going to be powerful, because let's take that to the next step and see why. So that means let me take this line here now, and this implies that 2b squared is equal to, by substitution of what a is, okay, we just said that a itself has to be an even number, which is, here's a, so I can actually put that in the parentheses here and say it's equal to 2k. All right. Now, remember all the things that we have recorded so far. We said that let's make sure that the rational number that we're claiming the square root of 2 is already in reduced simplified form. And if it is, then that means you can't there's no common factor between the numerator and denominator. The only way that could happen is either they're both odd numbers in the numerator and denominator, or one of them's even and one of them's odd. Because if they're both even, again, we could factor out a 2. So far, so good. Let's see where this leads us. Again, sometimes we need to take multiple steps. I already kind of know where this is going, so makes it a little bit easier for me, but a lot of times when we're conducting a proof, we're just searching for some weird thing to happen. So nothing weird has happened so far. Square root of 2, we just said, let's assume it's rational. Yes, we know it's not, but we're trying to prove that by assuming the negation and showing that the negation leads to a contradiction, something logical that just can't possibly be. So then we just did a legal math operation, squared both sides, multiplied b squared over, observed that there we got some information, and that important piece of information that we got here is that, hey, 2b squared has to be an even number. Well, that means that if two numbers are equal, the right-hand side has to also be an even number. And the only way that a number squared can be even is if the number itself is even. And now we're getting somewhere. Okay, so if A is even, remember we said that in reduced form, they are not both even. So yeah, that kind of leads to the conclusion that B must be odd. And we can kind of go with that. Well, hey, B must be odd, but let's see what happens. Let's simplify this. 2b squared equals, remember, 2k squared by definition is 2k times 2k, which is 2 times k times 2 times k, which is 2 times 2 times k, which is 2 squared times k squared, which is 4k squared. Okay, so that means the right-hand side simplifies to 4k squared. Okay, now let's divide both sides by 2 because I see that I can factor out a 2 from the left and the right. Divide by 2, and what do we get? Well, we get the statement that b squared is equal to 2k squared. B squared is equal to 2k squared. Well, wait a minute. Well, that implies that the only way, oh, notice this is an even number. And again, the same argument holds here. If the right-hand side is an even number, then this must also be an even number, which implies that b squared is even, which again, then would imply that b is even for the same reason that we wrote up here. But that's a contradiction, because we said that if that fraction is in reduced form, then that implies that one of them has to be even and one of them has to be odd. So we assumed that it was already in reduced form, but this claims, hey, you know what? It can't be in reduced form, but we know that we can reduce every fraction into reduced form. And since we know that A and B are not both even, this leads to a contradiction. B cannot be even, but it is. Right? So we can't have B being even and B not being even. We assumed that it was, we didn't assume that B was odd, but we established that A is even, and if the fraction A over B is in reduced form, then B can't be even, but the mathematical logic led us to the conclusion that B is even, and that's a contradiction. Therefore, the square rational is a false statement. If that's a false statement, since we know square root of 2 is one or the other, this leads us to the conclusion square root of 2 is an irrational number. And we are done. Now that kind of proof is not always satisfying in the sense that you didn't prove it directly, right? You didn't convince me that it was rational, but you not the direct way, but you convinced me that it wasn't irrational. And since it's not irrational, it must be rational. Now, proofs by contradiction can be challenging in this regard because sometimes we have to play around with the structure of things and arrive at a variety of conclusions. One of the things that would lead us astray, meaning that we would have a harder time with this, if back up here, where we wrote 2b squared equals a squared, well, that would naturally make us want to conclude, well, hey, a squared is even. And by definition, that would mean that a is equal to 2 times some integer. And that would lead us to the statement 2b squared equals 2k. And then you divide by 2 and you just get b squared equals k. That's a valid statement, but it isn't a useful one. So a lot of times we have to kind of milk the situation as much as possible, get every single detail, every ounce of information out of there, and play around with it further, sometimes digging into other things that we know that may not always be obvious and or transparent. So that is a proof by contradiction.